All right, this is visible, yes?
Yes, it is.
Thanks. Yeah, so as some of you may know and some of you may not, I have been on a quest to handle out-of-memory errors in Wasmtime and make Wasmtime robust in the face of um, the allocator returning null when you try to malloc something. So this is going to be just kind of a update on the status of that and a bit of motivation of why we're doing it and kind of what we've learned so far, etc. So the goal is to allow embedding Wasmtime into environments where the system does not kind of overcommit memory, like Linux kind of famously will, and where the allocator will return null if there isn't any more space for your allocation. And so the goal is that when the allocator gives us null, then we are going to return a recoverable error and kind of propagate that out to the embedder, whoever, whatever the embedder's kind of like public API that it called into Wasmtime with was. And we'll do this rather than panicking or aborting, which allows them to kind of free up space and try again, or otherwise do whatever they feel is best in this scenario. Um, so yeah, I mentioned rather than panicking or aborting because the Rust standard library, if you use that, depending on if you're using just alloc or you're using stud, is going to either panic or abort. And so by default, if you're using the standard library collections, that's what's going to happen. So the second question is kind of like, what code paths are in scope here? Is it going to be literally all of Wasmtime or just a subset? It is going to be just a subset. So I would say the boundary is not super, super well defined right now, and is mostly kind of driven by what the embedding that I work on actually requires. But basically, it's kind of all the stuff that works in no-stud builds. And so this is mostly like WASM execution. So loading and then running WASM binaries that you pre-compiled on some other system, which did, not need to deal with out-of-memory errors. And then also, you need to be able to call, WASI APIs. And so that means we also have to make WIT bindgen generated code kind of robust to OOM handling, as well as the Wasmtime WASI IO crate, which is sort of how you implement WASI in no-stud builds if you don't want to use kind of Wasmtime's default implementations. Eventually, we're going to have to get the component models kind of async concurrency runtime handling out of memory as well. That's going to be a bit of a tricky one. We'll talk more about that later. And then specifically, I'd like to call out that like getting all of Crane left to handle OOM is not a goal here. And compiling WASM in general is not a goal. It's really just running pre-compiled WASM. So our high-level plan was kind of basically to start with defining our own Wasmtime error type. So we used to use anyhow error. Now we use Wasmtime error. And it's API compatible. They're basically the same thing. And the migration across the version of Wasmtime that did that switch should hopefully have been pretty straightforward for people. But Wasmtime error also has kind of an out-of-memory variant. And it also handles allocation failure internally. And so when we have that in place, now we can actually go about kind of returning out-of-memory errors in various places. And so the big thing to do here is like, when are you allocating? Is because you have a collection. You need to put stuff somewhere, right? And so we can't use the standard library collections directly because, as I mentioned before, they're going to either panic or abort on OOM. And so what we're doing is we're defining our own vec type, for example, where vec push, instead of not returning any value, returns a result of either, unit or, hey, out of memory error, we would have had to resize the vector, but trying to resize it resulted in allocation failure. And then we also need a test harness for exercising OOM handling. We'll get more into this in a little bit later. And so all those things are done and landed. And so what's basically in progress now is just going through all the stuff that we need in Wasmtime and, going module by module, function by function, and switching things over to using the OOM handling vex, adding a OOM test for that code path and just, going until that passes and then we land that, etc. And then also, the plan is to start fuzzing the OOM handling and injecting an OOM on a random allocation or whatever, and making sure that Wasmtime doesn't crash, that we correctly report the OOM error, etc. So to talk a little bit about the error infrastructure. So this is the Wasmtime error submodule, which provides basically an identical API to Anyhow. And then a bunch of that stuff is also re-exported at the top level of Wasmtime just because you use it so much, like error, result, etc. And then there's also this out-of-memory error type, which the constructor takes kind of the size of the allocation that failed, and then you can get that, later on via this requested allocation size getter, if you want to like print, hey, we tried to allocate this much, but it failed. Um, and it was really important to make the size of this stuff as small as possible and able to take advantage of Rust's niche optimizations, like tight niche optimizations. And so we return, results all over the place. In particular, like result unit is probably the most common. And we want to make sure that that fits in one word, so that we don't have to allocate like, return buffers at the machine level ABI or anything like that, right? We can just use registers. And so the way we do that is, the struct error is a wrapper around this thing that's either an out of memory error or a dynamic like error, like any kind of error, right? Similar to like a din trait object. And so that's represented with a non-null pointer. The non-null is important because that's what allows the result discriminant to fit into the null bit and determine whether we're, in the OK or the error. And then or din error is, yeah, so it's a bit packed equivalent of either an out of memory error or a boxed in error. And the bit packing is when the low bit is set, it's out of memory, and otherwise it's a din error. And this is because din error has higher alignment than out of memory does. And then so out of memory, low bits always set, other bits are the allocation size. So, it's represented as this like non-null pointer, but it's not actually a pointer to anything. We never dereference it or anything like that. And so star mute din error is like star mute din core error, like a din trait object pointer. But a trait object pointer is a fat pointer. It's a pointer to the actual object, and then it's a second pointer to that object's v table. And so that's two pointers. That's too big, and it breaks our size goals here. And so din error is essentially a custom version of that moves that vtable kind of more in like the C++ style of putting the vtable into the object itself. And so we have these kind of two parallel structures, din error and concrete error, which have the same exact kind of prefix of fields in their repr so that they're always at the same location. But then din error has some trailing error, but we don't know what it is. And so we're never dealing with these things by value. We're always dealing with them behind some kind of pointer or reference or whatever. Whereas the concrete error has the actual error. And so we'll cast a concrete error to a din error. And so then all the stuff you need to ask about an error, like you can ask, is it this kind of type? Like, can I dynamically downcast it or whatever? That's going to call through the vtable. And then there's a trait error ext that is ultimately sort of like what we're calling. So everything that is in this like concrete error implements error ext. And so the way we get there is the vtable has this unsafe function that takes a din error, and then what it does is it has, when you create the vtable for a particular type, we get monomorphized versions of all these functions for that particular type that cast the din error unsafely to a concrete error of that particular type, and then call the trait implementation. And so it's, the unsafe bit is like making sure we have the right functions in the right places. Yeah, handling collections. We have a bunch of them landed in tree. We have vec, string, hash map, etc. You can look at all of that. We will need B-tree maps and B-tree sets, but we have not implemented them yet. And then basically whatever else we run into while adding OOM tests. Haven't seen too much of anything else, but this is where we are so far. All of this stuff is defined in two places, either crates core source alloc whatever, or crates environ source collections whatever. Generally, things are in crates environ source collections or whatever, but sometimes there's like an internal dep that is used both in CraneLift and Wasmtime, and that's the stuff that ends up kind of in core. You can always use them via Wasmtime environ collections because Wasmtime environ collections re-exports everything from the core crate. And then generally what we do is we don't implement the collection ourselves from scratch as much as possible. Instead, we're kind of wrapping over the standard libraries versions of these things. So for vec, we define a vec_t, but then the inner is just the standard library's vec_t, because the standard library provides an API try reserve. So when we reserve, we ask for whatever additional amount of space you need, and then we return a result based on that. And then instead of calling the inner regular reserve, which is going to panic or abort on OOM, we call try reserve, which does return an error. And then we turn that into an out of memory error and return that. And then push in kind of the standard library, it doesn't return anything. It's going to panic or abort on OOM. What we do is we will return a result of either a unit or out of memory. We'll do that reserve ahead of time. And then if that succeeds, we know we have space for the item, and then we push and it's okay. So by doing this kind of stuff, we don't have to actually implement all of the unsafe data structure and pointer manipulation and buffer ownership ourselves. Hash-based collections are a bit tricky though, because as far as I can tell, we don't really have a hard guarantee that if we do a self-insert after a successful reserve of one more space, that's never going to allocate. Because if there's a bunch of weird insertions that all end up colliding, right, that could require reallocating to redistribute all of the things. Been ignoring it so far. It hasn't been a problem in our OOM tests or fuzzing or anything like that at this point. And if we do run into that, then we're going to have a bunch of questions that we're going to have to ask ourselves. And I do expect we're going to run into this eventually, but I would like to make progress on the low-hanging fruit while I can. So I'm kicking this down the road or whatever. Additionally, an unfortunate bit is that our hash-based collections don't expose the entry API. And this is because the inner std types don't expose any kind of like try insert. They only expose try reserve. And so we can't, we don't have a way to kind of like wrap the entry API from std and do the like reserve before insert thing that we do. B-tree based collections are also going to be a little tricky because unlike vecs and hash maps, the B-tree types don't have any reserve or try reserve, and they also don't have try insert or whatever. So we can't actually just build a new type wrapper around them. But we really lucked out because it turns out we have a B-tree implementation in the Wasmtime repository already. And that's CraneLift bforest, and it's kind of arena based, which means that all of the allocation happens in that arena, and the arena is ultimately a vec at the bottom, so it's pretty easy to add, a fallible reserve and everything, and add fallible allocation to this B tree. So we really lucked out there. We also added a bunch of various like try traits that return a out of memory error on allocation failure, but otherwise are basically the same as traits from core, alloc, or stud in the Rust standard library. So Rust provides clone, we have try clone. It provides collect, we have try collect, etc. And then additionally, our SERDI serialization, deserialization implementations need to handle OOM. Luckily, that didn't require moving away from SERDI or anything like that, because when you're deserializing, which is when you're going to be doing the allocation, the error type that you return is a generic type parameter, but it's bounded by this like SERDI, deserialize error trait. One of its constructors that it exposes is custom, and so we can pass OOM through there, and it's not a problem. A little bit of a side on dependencies. Generally, they're a huge pain to use in code that must handle OOM because they don't use our OOM handling collections. They use the standard library collections, which will allocate without returning an out-of-memory result, that will panic or abort on failure. In general, they don't implement try-clone. They implement regular clone, and they will allocate inside regular clone. And so, unfortunately, we're really swimming against the Rust ecosystem's current here. I mean, you can see because we're implementing our own, try version of all the really base level traits, we're really kind of like forking off from the ecosystem at the very standard library level. So it's not great. We could potentially try and if we find other people who have similar use cases as us, we could try and create a shared sort of like try stud or something, and build like an ecosystem of people that are handling out of memory errors, perhaps. But luckily, our core WASM execution code paths are basically free of dependencies for the most part. And so this doesn't crop up too much in all the code that we actually care about handling out of memory in. As far as testing this stuff goes, this is very inspired by SpiderMonkey's, I forget what it's called, but their OOM testing infrastructure. So we have a custom global allocator, and this global allocator will artificially inject out-of-memory errors on a test. So like you give a test function, and it's going to run that function multiple times. And what it's going to do is it's going to inject OOM on the first allocation that it makes, and then check that it properly handled OOM and it returned an out-of-memory error correctly and everything. And then it's going to run that function again. And but this time it's going to let the first allocation pass, and it's going to inject OOM on the second allocation, right? And then it's going to do the same thing on the third and the fourth, etc., until the test completes and returns, okay, because all of the allocations succeeded. So small requirement is that tests need to be single-threaded here. We could lift that if we really needed to, but it hasn't been a problem so far. And yeah, as I mentioned, it's exhaustive for now. It does the first, then second, then third, then fourth allocation, etc. But the plan is when we get to, the fuzzing situation is to extend this existing kind of test infrastructure with an inexhaustive and kind of pseudo-random mode for fuzzing. So fuzzing will say, instead of exhaustively doing this function, just like do like the ith one, this random one, which is necessary because the fuzzing can't time out or whatever. All of these OOM tests live at crates fuzzing tests oom.rs. The test infrastructure is at crates fuzzing source oom.rs if you need to see that. Yeah, this is basically what one of the tests look like. Import the stuff. You have to set the special global allocator, and then you use this OOM test builder and run a test. And you can create a config and create an engine, and it will make sure that all of the allocations that happen inside of that closure are properly handling OOM. So where are we so far? So you can create like what code paths actually handle OOM. So creating a config, an engine, and a store all handle OOM. As far as running and loading core WASM modules, you can create a linker and define a function in the linker, or multiple functions in the linker. This whip, deserializing a precompiled WASM module, actually landed yesterday, so that's a checkbox. So you can deserialize a precompiled module, and we handle OOM there. So next up is going to be instantiating that WASM module, and then after that, executing the WASM module, and then got to do all that same stuff again for components, and then got to handle Wasmtime WASI IO and whip bind gen so that we can start covering WASI APIs. And then at some point, we're going to have to deal with the component model async runtime. And this one does really depend on the futures crate, at least right now. And the futures unordered kind of combinator within, which is like almost like a little mini async executor. I suspect the futures crate people don't want to add, fallible allocation try stuff to all their things because it's kind of gnarly and I don't know. So I suspect what we're going to have to do is cut down as much as possible on stuff that we use and then fork our own versions. But this is still up in the air and it's going to be a little while before we have to cross this bridge. So if people have opinions here, please talk to me, let me know. And then ultimately, the goal is for the Wasmtime crate itself to not have extern crate alloc anymore at all. And that doesn't mean that it can't ultimately link against alloc. So for those that don't know, alloc is the crate, the part of the Rust standard library that depends on a malloc-free implementation. And so we want to not depend on that directly, and instead only depend on our internal crates, which can link against that, but then expose the new type collections that return out of memory errors and stuff, right? So that when you're in Wasmtime, you literally cannot use something that's going to do the wrong thing. And I suspect that when we, flip that switch and remove the external crate alloc, there's going to be a long tail of stuff that is just, we didn't see it in the earlier processes, and we're going to have to go fix it at that point in time. So if this sounds like interesting work to you, I think at this point it is pretty parallelizable. And so if you want to help out, you can. Basically, all you have to do is choose a public API from the Wasmtime crate where it makes sense that we want to handle OOM there, right? So basically not compilation or whatever. So for example, creating a new resource on the host. And then go into the OOM test file and add a new OOM test that calls that API. And then run that test with logging for Wasmtime fuzzing enabled. And so what that's going to do is in the OOM test, whenever we inject an OOM, we log first the backtrace of where the allocation is happening, right? And so you basically just run the test with the logging, and then you see what the last backtrace was, and that's the place where you aren't handling OOM because you'll crash right after that allocation. And then you basically just need to switch that over to using OOM handling collections or whatever as necessary and propagate the out of memory as necessary. And then just run the test again. And pardon me. And just keep doing that until the test passes. And then now you can commit everything and send the PR. So yeah, that's everything that I had. And do people have questions or anything?
Yeah, there's quite a bit of activity in the Zulib. Ryan expresses support for tests. Um, Yash says, if you want, I can put you in touch with the Rest for Linux folks. They have very similar fallible allocation needs as Wasmtime and might be interested in collaborating on something like Tristed.
That would be really, really interesting to talk with them. At minimum, to kind of share experiences. But yeah, it'd be really cool to see where that goes.
Joel says, well, Joel edited his message. Um, Joel
Do
says,
you want me to just say it?
yeah, go ahead, Joel.
Sorry, sorry. Yeah, I edited the message because I seem to recall last time I looked at futures unordered that it was mainly just backed by a hash map or a hash set. Now taking a look just now, it looks like there's more to it than that. Uh, uh, Perhaps my suggestion stands, which is that we could look at forking it and creating our own OOM safe version as a start, and then maybe, think about upstreaming as a second step.
Yeah.
Excellent. Yash also says, if y'all switch to futures concurrency, that he'd be happy to add support for fallible allocation behind a flag, and the equivalent to futures unordered is future group.
Okay. Yeah, I'm not super familiar with future concurrency, but let's talk. If it's gonna make our lives easier, which it sounds like maybe, it sounds like it's worth investigating.
Bailey says, I wonder how much work the Wasmtime WASI IO step is, and if it's worth considering scoping to just P3.
Um,
I
well,
actually offered an answer to that. Sorry to interrupt, Nick. Which is, I mean, first off, Nick, you're doing a really great job on this, and this is a ton of work. So thank you. I think doing Wasmtime WASI-IO is relatively small compared to many of the other things you did. And also it just happens that for our embeddings, we need P2.
yeah. Joel, I see you have your hand up.
Yeah, it's a new topic. So if we're done with that one,
Yeah, go ahead.
maybe we are. So I was just thinking in terms of kind of the big picture here with P3 and whatnot, there is a lot of code in kind of concurrent.rs and futures and streams.rs and whatnot. I can't think offhand how much more besides the futures unordered, which is indeed the core of it. But I'm wondering if part of the strategy here might be kind of taking a cue from Chris's presentation to kind of push some stuff down into components, potentially part of the component model async implementation could itself be a component. And this actually alludes back to Luke's presentation yesterday, where he was talking about this lower component idea, and part of that, which I'm planning to write an RFC for, would be this idea that you could take create a component lowering thing that could embed code that does the P3, the component model async stuff, bookkeeping and whatnot, task juggling in the component itself, and thus, this lowered component could then run on a relatively simple core WASM runtime. And I'm wondering if we could kind of take a step towards that. I don't know if you've thought about that, or if what you think of that.
I haven't thought about it in the context of OOM handling. I am, in general, a fan of self-hosting, as you might guess. We've talked about this before in terms of part of the Wasmtime's GC implementation. So right now, our free list implementation is not super great. Don't need to get into details there. But one thing we identified could work out really well would be essentially compiling DL-malloc to WASM, and then using that as our free list implementation and sort of like self-hosting a lot of the GC. So yeah, there's a lot of stuff that's sort of interested in this space, and it would be great to like push towards that wherever we can.